A NASA spacecraft is set to make history today, getting closer to the sun than any other human-made object.
It began with a single cryptic announcement from the depths of the scientific world that left the global community stunned. NASA, known for its cautious and calculated communication style, broke its usual mold to unveil a revelation that sounded like something from a distant future or the pages of a science fiction novel. They had created something so advanced, so far beyond current technological understanding, that it was capable of reaching light speed, a feat once thought entirely impossible under the known laws of physics. Before we start, smash the like and subscribe buttons for more updates. At the heart of this development was an experimental propulsion system, an engineering marvel born out of decades of theoretical work, black-budget projects, and relentless trial and error. Internally referred to by researchers as the LS drive, this breakthrough was not an incremental improvement in propulsion, like nuclear or ion drives, but a wholesale leap into a new regime of movement. The LS drive was reportedly not dependent on traditional combustion or reaction-based principles. Instead, it leveraged an exotic form of field manipulation, a theoretical physics concept that, until recently, existed only on chalkboards and speculative papers. The foundation for this advancement came from years of research into quantum field fluctuations, negative energy densities, and space-time curvature manipulation. To understand what made this so revolutionary, one needs to consider the fundamental barrier imposed by Einstein's theory of relativity. As an object approaches the speed of light, its mass becomes infinite, and so too does the energy required to move it. This was long considered the ultimate speed limit of the universe. NASA's new technology didn't break this rule in the conventional sense. It found a workaround. By exploiting the geometry of space-time itself, the drive didn't move the ship through space at light speed, it moved space around the ship. It was less like a car accelerating on a road and more like a rug being pulled beneath that car at impossible speed. The origins of this concept trace back to the Alcubierre drive, a theoretical propulsion method proposed in the 1990s. The idea was to create a warp bubble that compresses space in front of a spacecraft and expands it behind, effectively allowing faster-than-light travel without violating relativity. However, Alcubierre's model demanded massive quantities of negative energy, something that remained beyond humanity's reach until now. NASA's announcement confirmed that the LS drive utilized a controlled and scalable form of what was dubbed Casimir negative vacuum energy, harnessed within a custom-built containment matrix. The laboratory tests reportedly involved microscopic warp bubbles, mere nanometers in size, which were expanded and stabilized using a complex interaction of laser interferometry and cryogenic superconductors. The first major breakthrough was the successful formation of a stable bubble that moved within a vacuum chamber, producing measurable displacement effects. It was the first time matter was observed to move without applying conventional thrust, as if the very space it occupied shifted it forward. What followed was a cascade of milestones that escalated over a span of just 3 years. From controlling movement within lab environments to building a prototype craft capable of operating in low Earth orbit, NASA gradually scaled the technology. According to internal sources later confirmed by official documentation, an unmanned craft dubbed Starlance 1 was fitted with a scaled-up LS drive core and launched into orbit from a classified facility. Within seconds, it disappeared from all standard tracking systems, only to reappear thousands of kilometers away, in a trajectory consistent with near light-speed displacement. The implications were staggering. Humanity had taken its first real step toward interstellar travel. The stars, those unreachable points of light we had only observed, suddenly felt close. Planets orbiting Alpha Centauri, previously accessible only through robotic missions that would take decades, could now theoretically be reached within months or even weeks. Proxima b, once a distant object of speculation, was now within reach of direct exploration. From a technical standpoint, the LS drive relied on what NASA scientists called localized space-time gradient manipulation. The ship didn't gain mass as it approached light speed because it never truly moved in the traditional sense. Instead, a localized field around the craft allowed it to remain stationary relative to its immediate space-time pocket, while the universe itself warped around it. The boundaries of this bubble were kept stable through a synchronized network of gravimetric regulators and energy field actuators, fed by a power source that, although not detailed publicly, was hinted to be a next-generation zero-point energy module. There was, of course, no combustion, no propellant trails, no jet emissions. The craft was eerily silent and emitted no detectable radiation save for faint gravitational ripples measured by ultra-sensitive detectors. Traditional Newtonian physics broke down at the operational edge of this phenomenon, and entirely new equations were developed to predict and control the motion parameters. One of the most astonishing aspects of the announcement was that the LS drive had passed all safety benchmarks for human operation. Radiation shielding, previously a significant hurdle for any relativistic travel, was no longer necessary in the traditional sense because the warp bubble protected the occupants from external space-time interactions. Inside, time flowed normally, no time dilation, no relativistic mass effects. Astronauts could, in theory, traverse dozens of light years while only aging the same amount of time as experienced on Earth. The relativity barrier had been not merely approached, but sidestepped altogether. International observers reacted with a mix of awe, disbelief, and cautious optimism. Other space agencies, particularly in Europe and Asia, were quick to request collaborative involvement. Independent physicists scrambled to examine the data, much of which NASA had made available under a surprisingly transparent publication protocol. Peer review confirmed what had previously been unimaginable. The data was real. The energy readings, motion vectors, and gravitational metrics could not be explained by any known conventional propulsion system. The implications extended beyond travel. The ability to manipulate space-time suggested possible applications in communications, energy transfer, and even planetary defense. If space could be warped to move a ship, it could theoretically be warped to shield a city or redirect high-energy objects. Additionally, the energy-efficient nature of the LS drive opened the door to sustainable off-world colonization. Transporting heavy equipment, resources, or even entire habitat modules to Mars or the Moon could become as routine as launching a satellite today. Perhaps most profound was the philosophical and existential shift this discovery triggered. For centuries, humanity had looked to the stars with longing, limited by the vast gulfs between them. Now, that barrier had been pierced. The boundaries of exploration were redefined. No longer constrained to our solar system, the next generation of astronauts, scientists, and dreamers would grow up in a world where interstellar travel was not a fantasy, but a mission objective. The initial announcement concluded with a striking statement from the project's lead physicist. Though the quote itself was not the focus, the idea behind it resonated. The message was simple: we are no longer bound. Earth is our origin, but it is no longer our limit. It echoed not just within scientific communities, but throughout every society on Earth. For the first time, the idea of becoming a truly spacefaring civilization had shifted from theoretical ambition to actionable reality. Academic institutions rushed to adapt curricula. Physics departments were overhauled. Entire new fields of study emerged overnight, including applied warp dynamics, relativistic spatial architecture, and interstellar field navigation. The race to train the next generation of warp engineers had begun. Simulators were developed based on the LS drive's operating model, allowing students and professionals to experience controlling a ship not through thrust, but through the articulation of space-time curvature. It was a completely different way of thinking about movement, orientation, and space. Behind the scenes, a deeper layer of implications was being unraveled. The possibility that warp technology could detect or interact with substructures of the universe previously invisible to us, such as higher dimensional fields, parallel timelines, or dark matter currents, became a topic of intense speculation. Some theorists even suggested that the LS drive's manipulation of space-time could function as a new kind of sensor, offering glimpses into aspects of the cosmos previously inaccessible through traditional observational tools. There was also an undercurrent of cautious intrigue regarding potential extraterrestrial implications. For decades, many scientists and theorists had speculated that faster-than-light travel was the key to contacting or discovering alien civilizations. Now that barrier was gone. If other intelligent beings existed in the galaxy and had developed similar technology, the odds of encountering them or at least observing their activity had increased exponentially. What once required billions of dollars and years of planning could now be accomplished in days, possibly hours, with precision never before achievable. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on NASA creating tech that might reach light speed? We want to hear from you. Thank you for watching, and see you next time.